In this problem, we note that the function successful pairs receives two array of integers, spells and potions, and the variable success of type long, which can store large integers. The array spells has length n and potions has length m. An element spells of I represents the power of the ith spell, and potions of j represents the power of the jth potion. A pair spells of I potions of j is considered successful if the product of their powers is at least equal to the success value. The function should return an array where each element represents the number of potions that form a successful pair with each spell. To solve this problem efficiently, we use the lower bound binary search in the algorithm. First, we sort the potions array in ascending order. Binary search requires the data to be ordered, and lower bound allows us to quickly find the first element in potions that, when multiplied by the current spell, is large enough to satisfy the condition spell times potion is greater than or equal to success. If the potions array were not sorted, we would need to loop through the entire array for each element in spells, checking if the condition is met. This would increase the algorithm's complexity to O of n times m, where n is the size of the spells array and m is the size of the potions array. By sorting the potions array and using binary search, we reduce the complexity to O of n log n plus m log m. The initial sort has a complexity of O of m log m, and for each element in spells, the binary search in potions has a complexity of O of log m, which is much more efficient. We initialize an empty array ans to store the final results, which are the number of valid pairs for each element in spells. We then loop through all the elements in spells using a for loop. For each element v in spells, we use lower bound to find the first position in potions where potion is large enough such that v times potion is greater than or equal to success. To avoid division errors, we convert success to a real number by using success times 1.0 divided by v. We then find the first item in potions that has a value greater than or equal to this converted value using lower bound of potions that begin, potions that end, and value. We calculate the index of this element in the potions array. All elements from this index to the end of the potions array will form valid pairs with v, so the number of valid pairs is m minus I, where m is the size of the potions array. We store this result in ans. After looping through all the elements in spells, we return the array ans, which contains the number of valid pairs for each element in spells. In conclusion, this algorithm efficiently finds pairs of spells and potions that satisfy the given condition using sorting and binary search. Sorting the potions array allows us using the lower bound function to quickly determine the position of the first valid potion for each spell. This approach reduces complexity and ensures that the desired result is achieved efficiently, making it well suited for searching and selecting problems in sorted collections. Now, it's time to validate this code and ensure it operates correctly. You are encouraged to test different scenarios, including edge cases, to confirm the solution and enhance your understanding and problem-solving skills.